Hello everyone, my name is Sashank Santanam and I'm a first year PhD student working as a research assistant at the Charlotte Visualization Center. My topic for the application level presentation is titled LSTM, a Search Space Odyssey. This paper was published in the year 2015 and it provides an introduction to what an LSTM is, along with the different variants of LSTM, and also provides us with a performance comparison of LSTM across three different datasets. In my previous video about text classification algorithms, I introduced what a vanilla neural network is and how it functions. One of the major limitations of a vanilla neural network, and we could also consider convolution neural network, is that their API is too constrained. What do I mean when I say it's too constrained? It's that they only accept a fixed size vector as input and produce a fixed size vector as output. Example would be like a probability of different classes. Not only that, these models perform a mapping using a fixed amount of computational steps. One of the core reasons why we go for a recurrent neural network is that it operates over a sequence of vectors, sequences in the input, sequences in the output. In the diagram shown, let us consider A to be the neural network structure, which it takes in some input x of t and it produces an output h of t. We use a loop to make sure that the information is passed from one step of the network to the next. If you take a look at the image closely, we see that a recurrent neural network is not different from a regular neural network. A recurrent neural network can be thought of multiple copies of the same network, each passing a message to its successor. We show a small equation how the way each activation function is calculated with the help of sigmoid, and in the last layer you can use a softmax to get the probabilities. In this slide, we take a look at the different applications of RNN and what architecture is used to solve a particular application. The first architecture is the image captioning. In the image captioning, we provide a image as the input, and this image is processed with the help of a convolutional neural network. Before we use a recurrent neural network to caption the image with an appropriate one. The second architecture which we use is for sentiment analysis, where a sequence input is provided as the input, and output would be either classifying the sentence which was provided either as a positive or negative. The third architecture, which is shown in the figure, is for machine translation. So machine translation is where you can convert it from English to French or English to any other language or between any two languages. So we provide a sentence as the input, and then we do a encoding phase, and from the encoding phase it goes to a decoder, and from decoder it produces output in a different language. The last architecture which is shown is for the video frame level analysis, where we analyze each video frame by frame. There are three major issues which faces every neural network. The first issue is called as vanishing gradient, and it is a difficulty found in training certain artificial neural networks with gradient-based methods such as backpropagation. In particular, this problem makes it really hard to learn and tune the parameters of the earlier layers of the network, and this problem becomes worse as the number of layers in the architecture increases. The second issue which a neural network faces is the problem of exploding gradient. This occurs when the gradient value grows extremely large and it causes an overflow. However, this problem is easily detectable at runtime. The last problem which every neural network faces is the long-term dependency, and this long-term dependency primarily affects a lot of natural language processing tasks. Going more in depth with regards to the problem of exploding and vanishing gradients. In the problem of exploding and vanishing gradients, we take the derivative of the error at each time step. That is, at each time step, it is represented with regard to the summation of t from 1 to capital T. The error at each time step is computed through applying the chain rule differentiation. Now that we know what issues face a recurrent neural network, we need to find methods to overcome it. In order to overcome the problem of exploding gradient, we use a method called as clipping the gradient. So clip is where we use a threshold, and if a gradient goes past a certain value, we clip it and we use the threshold value. In order to overcome the problem of vanishing gradients, there are two techniques to do it. The first technique is initializing the matrix randomly, and the second technique is to use rectified linear units instead of sigmoid functions. Derivative of a rectified linear unit is either 0 or 1. This way, the gradients would flow through the neurons whose derivative is 1 without getting attenuated while propagating back through the time steps. Now that we know what an exploding and a vanishing gradient is, we need to take a look at the third issue facing neural networks, that is long-term dependency. Long-term dependency typically affects every natural language processing task. So let us take a look at it with the help of an example. Consider the sentence, I grew up in France and I speak fluent French. So we need to predict the word French in this sentence. So in order to do this, we need certain information from the input, and one of the key information which we need to keep a track of is France. So this is just a simple sentence, but assume it's a big paragraph of 100 pages. So assume the last page there's an information which is dependent on the information present in the first page. So as a gap between the neural network grows, it becomes unable to connect the information. So this is where the long-term dependency issue comes into play. So how do we overcome the issue of long-term dependency? We overcome the issue of long-term dependency with the help of LSTM. LSTM is called as long short-term memory networks, or people just usually refer to as LSTMs. LSTMs are just a special kind of RNN which is capable of learning long-term dependencies. The LSTM was introduced way earlier in 1997, and over a period of time they were refined and made popular in a lot of natural language processing tasks. The LSTMs work very well on a large variety of problems. So the LSTM architecture is designed in such a way that it avoids a long-term dependency. Remembering information for a long period of time is practically the default behavior because there is something in the architecture which helps in this process. The following diagram shows the LSTM architecture. In this diagram, the pink circles would represent the pointwise operations and the yellow rectangle box would represent the neural network layer. And every arrow is a vector transfer. So what is the core idea behind LSTM? The core idea in LSTM is the cell state or the horizontal line which runs through the top of the figure. The cell state is like a kind of a belt. It runs through down the entire chain with only some minor linear interactions with the help of the pointwise operations. So the LSTM does have the ability to add or remove information to the cell state, and this is done with the help of the structures called as gates. Gates are a way to optionally let information through, and they are composed out of a sigmoid neural net layer and pointwise multiplication operation. The sigmoid layer outputs numbers between 0 and 1 describing how much each component should be led through. A value of 0 means that nothing is led through, which means that the the cell would be able to forget it. And LSTM has 3 gates. One is to protect and control the cell state. So the first gate in the LSTM architecture is called as the forget gate. The forget gate is depends on what information we are going to throw away from the cell state. This decision is made with the help of a sigmoid layer. So it takes a look at the previous output from the previous cell and the current input and outputs a number between 0 and 1. With the help of this 0 and 1, we will be able to know whether the information which we are going to pass to a cell state is needed or not. A value of 1 represents that we need to completely keep this, while a value of 0 says that we can get rid of this information which is being passed. The next gate which we are going to look at is called as the input and the update gate. The input gate is done with the help of a sigmoid layer which decides what values which we need to update, and the tanh layer creates a new set of values between -1 to 1, and this -1 to 1 is then passed on to the cell state where the values to the cell state are updated. So the next part of the LSTM which we are going to look at is updating the cell state. So the cell state is updated with the help of the pointwise vector operations. So the first operation which the cell state undergoes is the multiplication with from the forget layer. So the forget layer produces, with the help of sigmoid, produces a value between 0 and 1. So all the values which are close to 0 are those values which we don't need to remember, and all the values that are close to 1 are those which we need to remember. And when we multiply the cell state by these values, we forget the information which is not needed. The next part of updating the cell state is by multiplying the input gate and the output gate together. This in turn creates a new vector which needs to be added to the cell state. So the last gate which we are going to look at is called as the output gate. The output gate will be based on our cell state, but it will be a filtered version. So first we have a sigmoid layer which decides what parts of the cell state we are going to pass. Then we put the cell state through a tanh function which produces a value between -1 and 1 and multiply it by the output of the sigmoid gate. So we only output the parts which we need to. There are three popular variations of LSTM architecture. So the first one is the LSTM with people, the next one is the LSTM with coupling, and the last one is the gated recurrent units, which was invented pretty recently. In this diagram, the LSTM with people connections is shown below. One of the major differences between a simple LSTM and LSTM with people is that the gates are allowed to take a look at the cell state in LSTM with people. So the next LSTM which we are going to take a look at is the LSTM with coupling. In the LSTM with coupling, the input and the forget gates are coupled together and the decisions between them are taken at the same time. So we only forget when we are trying to input something in its place, and we only input new values to a state when we forget something older. So the last variant of LSTM which we are going to take a look at is called as the gated recurrent unit. The gated recurrent unit was invented by Cho and others in 2014 and is one of the most popular variants of LSTM. It combines the forget and the input gates into a single update gate, and it also merges the cell state and the hidden state and also makes a few other changes. The resulting structure of this gated recurrent unit is simpler than what an LSTM is, and sometimes in certain cases it is faster than LSTM. So in this slide we show the architecture of a gated recurrent unit. The gated recurrent unit has four main gates. The Z of t is an update gate, the R of t would is a reset gate, the H bar of t would is a new memory, and the H of t represents the hidden state, and the equations are shown besides each gate. So the first one we're going to talk about is the new memory generation. A new memory H bar of t is the consolidation of the new input word x of t with the past hidden state, which is represented by H of t minus 1. So the reset gate is represented by R of t is responsible for determining how important H of t minus 1 is to the summarization of H of t. The reset gate would also have the ability to completely diminish the past hidden state if it finds that it is completely irrelevant for the new memory. The update gate is probably the most important gate, and it is represented by Z of t, and it is responsible for determining how much of the H of t minus 1, that is a previous cell, should be carried forward to the next state. For example, if the value of Z of t was approximately close to 1, then H of t is almost entirely copied out of H of t minus 1. Conversely, if the value was close to 0, then the new memory H of t is forwarded to the next hidden state. So the last one is which we are going to talk about is the hidden state. The hidden state is finally generated using the past hidden input H of t minus 1 and the new memory generated H of t with the advice of the update gate. So now that we have seen the different variants of LSTM and also with the basic LSTM, a performance comparison was done on three different datasets. The first dataset is a speech corpus dataset called as TIMIT, and it is largely responsible for speech recognition process so this is for any speech recognition model. The next corpus which we are going to take a look at is the IAM Online, which is the online handwriting database, and it consists of English sentences as time series of pen movements that have been mapped to characters. The last dataset which the authors of this paper took a look at is the JSB Chorales dataset, which is used for music modeling. The pre-processed data consists of a sequence of binary vectors, and the task is next step prediction. The next thing which we're going to take a look at is the hyperparameter search. The hyperparameter search in this paper was a random method which was used. The main reason for using the random method was that it was easy to implement and it was trivial to parallelize, and it covers the search space in a uniform way. And in this paper, the authors did 200 trials, and for every hyperparameter, and there are a total of 4 hyperparameters, and each had its particular set of range to cover. And the table shows the all the different hyperparameters which were tuned by the authors. Comparing the performance of the different LSTM variants, it was found that there isn't much significant difference between each one of the individual variants. It is said the TIMIT and the JSP Corals dataset had an error rate of 29.6%, and the IAM online dataset had a character error rate of 9.26. Using a peephole LSTM or a coupling LSTM did not change the results, or there wasn't any significance. So one of the primary takeaways is that pre-processing plays a major role. So the conclusions from this presentation are that the RNN offer flexibility in design. Using a simple RNN or vanilla RNN is not good. We need to be aware of exploding and vanishing gradients. We can use LSTM and GRUs to avoid the issue of long-term dependency. We can use a clip method for the exploding gradient, and for the vanishing gradient we can use RELUs or random initialization. We also need to tune the hyperparameters properly, and the forget and the output activation are critical components.